Welcome to the afternoon session, and this is for the M-LEEaD Environmental Statistics Day Symposium, and that was hosted by our Integrated Health Sciences Core at M-LEEaD. And this Integrated Health Sciences Core was co-led by Professor Marie O'Neill there, and then Professor Sang-Young Park and myself. So it's really up to their support to have these events over the years. Let's give them a applause. So in this afternoon, we will have 3 invited speakers, and all of them are our junior faculty rising stars. Let me put this. And we'll first have Professor Zhenke Wu from our Department of Biostatistics, and then we'll have Professor Liyue Shen and Professor Qing Qu from the EE and Computer Science. So I'm going to introduce Zhenke first. So Zhenke is a professor, associate professor now. Just promoted. Congratulations. Yeah, so he completed his bachelor degree in math at Fudan University in 2009 and a PhD in biostatistics from Hopkins in 2014, and then stayed at Hopkins for his postdoc training. Zhenke is currently an associate professor of biostatistics at the University of Michigan. He is also a faculty affiliate at MIDAS, Michigan Institute for Data Science. His research involves the development of statistical methods that inform health decisions made by individuals. He is particularly interested in scalable Bayesian methods that integrate multiple sources of evidence with a focus on hierarchical latent variable modeling. Zhenke also works on sequential decision-making, reinforcement learning, and micro-randomized trials. He actually gave a talk about the micro-randomized randomized trial at our environmental health science statistics sequence for the seminars. Zhenke has developed the original methods and software that are now used by investigators from the research institutes such as USCDC and Johns Hopkins, as well as side investigators from developing countries, for example, Kenya, South Africa, Gambia, Mali, Zambia, Thailand, and Bangladesh. Very, very impressive. So today, he's going to share some of his thoughts on this, what can AI offer for environmental health sciences. So let's welcome Professor Wu.
Okay, good afternoon, everybody. Thanks, Lu, for introducing me very kindly. So Lu is actually my faculty mentor, so it's no wonder that you heard me. I'm always assistant professor, but thanks for helping with the promotion. So today, I think we have a wonderful session. In my view, we have 2 wonderful speakers from ECS, and I view my role as more of like starting the conversation and facilitating the discussion. And in terms of have I done some work in this area? So I do publish one environmetrics paper. So I consider myself have little experience in relating statistics and environmental health. But I think today I'd like to make it more expansive in the sense that can we think together? Can we discuss what are the opportunities of what we call AI? How can that help environmental health science? And so what I'm going to do is to provide some high-level kind of discussion points, and then the next 2 speakers will provide more in detail, showcase of what they are doing. Hopefully, this will spark your interest, and hopefully there will be some downstream collaborative opportunities. A little bit about myself, maybe too much, as I do some methods of research and applied research. And I do lots of Bayesian latent variable models. And the second one is sequential decision making, especially when it's involving like reinforcement learning, causality stuff. And third, I'm increasingly convinced that machine learning and statistics, this intersection is where classically trained statisticians can really shine. And I think there are lots of questions how to integrate the two to conduct good inference. And there are other considerations that can be formulated in statistical terms. For example, how do we think about fairness in this kind of context? For applied research, I do a lot of what I call interventional mobile health. I don't see other people calling it. Other people maybe calling it digital health, but to us, it's more about how do we, have people look at their cell phone and we pin them, and hopefully we can sort of encourage them to maintain healthy behavior. For example, to keep walking, if they have the chance, or to have them practice some mindfulness exercise. And then I have some other work related to wearable device data and some data science work in low and middle income countries. So for the reason why we get together here, partly is because we were somehow bombarded by this, set of news that AI is now going to replace many different things. And I think that the talk Jason gave this morning actually showcased that there are lots of possibilities of actually automating a lot of, routine tasks we can do. So just to remind you that ChatGPT came out in November 22nd, right? So these articles are like written in 2023. Lawyers are worrying that they're going to lose their jobs and what have you. And for example, teachers are going to be replaced because GPT-4 extremely good at explaining things very slowly in detail. So all these questions brings about the excitement, maybe hype. There's this shiny method that's called AI, or large language model, and there are people who are trying to use this method for their own research. And I think going back to today's theme, we're going to think about what are the possible dimensions we should consider, and what are the kind of general framework we should think about AI in this kind of environmental health context. So this is a quick outline. So I will list, based on my understanding, what are the major scientific questions in EHS. I'm pretty sure there will be other questions that can be added to this list. The second one is just a quick comparison of the AI techniques. I broadly divide that into probabilistic modeling and algorithmic methods for function approximation. And third are the ethical considerations. Fourth are some low-hanging fruits, and especially large language models for data and code products. And what are the barriers and what we can do, and finally some discussion points. And by the way, this is geared towards helping you guys to discuss these kind of synergies between AI and EHS. So what are the scientific questions? So actually, I did some quick Google, right? So I basically was putting in what are the AIs in environmental health science. I found two documents. The first document is the National Academy of Sciences. Actually, I believe Professor Moore was in that workshop. So I actually got a lot of wisdom from that report. So a second report actually is from, I think, a Research Triangle collaborative report. So I think it's in 2018 or something. So, that predated ChatGPT. So people have realized that AI can be very powerful in sort of integrate different types of data to help, advance environmental health sciences. So what are the kind of questions that I saw in those kind of reports? The first one actually I did not see quite a bit, but I still want to point out that there are people who are trying to apply machine learning AI to climate change related questions. And this person wrote this paper that's very comprehensive. The second bullet basically is like predicting chemical toxicity, and I think these are classical questions: how to address chemical mixtures, do source apportionment, and how do we sort of incorporate many different biomarkers exposure. And of course, there are questions of how do we estimate exposures, right? We know certain exposures are important, but how can we measure them? How can we estimate them? There are questions about dose response analyses, and finally, gene environment interactions, and how do they contribute to disease risks? And there are clearly many more questions. So what are the data type I saw based on some quick Googling? So I see spatial temporal data. They're broadly related to like climate data. So they can be, some data from transportation, building cities and farm and forests. And they're also like, sensor data that's like cheap sensor data that are placed in local areas, and they can detect, say, PM 2.5 levels, and they can be used to study how pollutants would impact disease risks. And the data we saw often very high dimensional correlated. For example, if you have many different chemicals, they can be, if you calculate correlation, they're very high. And actually, the methods paper I mentioned that worked on is basically how do we do a lasso with the acknowledgement that many chemicals are highly related. How do we do the grouped version of that? And many of these measurements have errors, right? And finally, I think more and more common, we have multiple clinical outcomes we need to relate to these exposures. And returning to AI, I will have a exercise to define what is AI. So in general, in my view, there are 4 different kinds of training method. And I think that historically, the first one, the supervised learning, has been extremely successful. It actually means that we have the labels of different instances, and we want to train a model that minimizes certain kind of loss that would indicate highest possible accuracy. And lasso is one prominent example. And actually, for the students here, I would ask you to ask yourself, what is L, what is A, what is S, what is the second S, what is O? But that speaks to the popularity of how this method has been. You may not even know what actually the second S represents. So the second type of training algorithm is called unsupervised learning. I work a lot in this area, so people call this clustering, has been very prominent in especially omics analyses. And there are this kind of a mixed breed called semi-supervised learning. This is often happening in the case where obtaining a label, gold standard label, is extremely expensive and cumbersome, and people have devised ways to learn from the subset of data that has a label. The third one, it's a training method called self-supervised learning. This has basically contributed to the success of the current wave of large language model. What people do is basically to have the training data as, say, a text, and they will basically mask, individual words. And if the model has been trained in a way that it can predict the masked words well, then they say it's a well-trained model. And clearly, there are questions about, is this kind of self-supervised learning really intelligence? So I was listening to a talk. Basically, imagine one situation. So you're reading a detective novel, right? So it has 500 pages. So the final sentence is, the person who killed these 3 people are blah, right? So if the large language model under this training can figure out that name, so the question to you guys is that, does that represent intelligence? I think to me that's pretty amazing, that it figure out all the complicated plots and it predict the name correctly. So there are lots of debate about whether such kind of training and models are representing human level intelligence reasoning. There are different schools. I will not discuss too much about that, but just remember that example, that predict the name in that final sentence of the detective novel. It's pretty amazing. Finally, reinforcement learning. So this is a different kind of machine learning. Usually it's called the cherry on the big machine learning cake. It's very hard to do, requires a lot of data. We're not going to talk about this. The reason why we list all these is to show you all the major kind of training methods or things people in AI and machine learning have been working on. So it doesn't hurt to list a few methods and make the contrast. I want to make the point that, for certain applications, there are places for probabilistic modeling, and there are reasons for using algorithmic methods. So if you have been to Professor Moore's talk, you have seen many names, right? They have different kind of menus. You can let the AI to choose what is the most appropriate method. So I'm just going to list some of them. So on the left column, these are the probabilistic modeling techniques. They include like Bayesian network. People call this directed cyclic graph, DAC. And you can do like causal discoveries among the variables on the nodes. And also there are multi-level modeling, right? Mixed effects models is basically a more general term to that. You can model within person heterogeneity and between people heterogeneity. There are like time series regression, right? If you are doing pollution and health related research, a common question is that how does the air pollution in the past few days would impact the mortality for people over 65 years old, and those require time series regression. Sparsity regularized method lasso, dimension reduction techniques like factor models, Gaussian processes, right? If you want to model spatial distribution of certain real valued quantities or discrete value quantities, you can use a generalized version of it. And finally, causal inference. Causal inference is basically a missing data problem. If I take the pill, you will not see the version of me that I did not take the pill. So to do causal inference means that contrast me against me, but only the treatment is applied or not applied. So that's inherent missing data problem. Usually the assumption requires you require some probabilistic statement about how these two outcomes are related. And now I think that there are lots of literature that says classical causal inference method can be augmented by machine learning methods. These are generally called double machine learning. I think some of you may run into it if you are working on this kind of problems. On the right column, I do not even need to mention these: random forest, SVM, gradient boosting. That's what XGBoost was implementing neural networks, and deep learning or large language model. So large language model really is just a special case of deep learning. Deep learning is a special case of machine learning, and large language model usually designed for sequence data like texts. Right? So in many of the health-related studies, we really want to get to the causal question. Is this person exposed to the if the person is exposed, then does that cause this person to have a higher risk of having disease? So as I have mentioned, causal inference essentially is a missing data problem. We require assumptions. And that assumption usually can be characterizing how we design the study, how we collect the data. And that's usually where the probabilistic modeling is absolutely critical, because it can incorporate lots of design-related considerations like case control studies or cohort designs, what have you. So I would say both sets of methods have their place of application. And on the right-hand side, people have been using them because it's wonderful for doing functional approximation. If I care about prediction, right? Input a bunch of exposures or covariates, let's output as accurate as we can the prediction. While on the left-hand side, this has been a classical framework for statisticians who are focused on inferencing, doing inference, like estimating the causal parameter or estimating, say, beta 2, right? So I did also a quick Google Ngram viewer. So you can notice a few different words. Statistics was invented around 1900s by the person, I think, popularized by Fisher. And so it has experienced a lot of growth and somehow has declined a little bit in terms of at around 1980s. And if you look at the artificial intelligence, which is a red line, you can see that it has hit a peak at maybe at the second half of the 1980s. Do you guys know what happened there? So it's because people were working on neural networks. And then that died down a little bit because somehow neural networks at that time was not easy to train, and it's complicated. And people working on neural networks were treated as like weird. At that time, people were working on symbolic logic kind of framework. But then it experienced a huge surge, partly because of the success of deep learning. And machine learning, it's the dark green line. It has overshoot every keyword here. And I'm also putting bioinformatics here as a comparison. It's relatively flat. And for the environmental health, I actually tried environmental health statistics or science. Actually, that line is extremely low. So I'm just going to present environmental health. So I don't know what happened around here, but there seems to be a dip. I actually have no idea. If anybody has any idea, let me know. So this speaks to how people are paying more and more attention to artificial intelligence and machine learning. Being a statistician, clearly I feel that they're probably borrowing a lot of the techniques from statistics, but they're calling this artificial intelligence machine learning. So, and I was like clearly trying to define what is AI, because my view is that AI draws a lot of techniques from statistics, but they do have their own kind of extremely important contributions, especially in system engineering problems. I think in the morning that Professor Moore's talk is illustrating how important it is to have a very good systematic design. So it's not only about statistics. I can give you like 30 seconds to read it if you want. I don't agree with everything. For example, I don't agree statistics is a branch of mathematics. So if you apply for NS funding, actually we apply to this division called Division of Mathematical Sciences. A lot of statisticians protesting this. But anyway, I think this is what the data on internet says. So the key difference lies in their scope and application. AI aims to create systems capable of performing tasks that would typically require human intelligence, often using insights and methodologies from statistics. Whereas statistics focuses more on making inferences and prediction based on data without necessarily aiming to replicate human cognitive abilities. I'm not treating that as a right answer, but just for you to know what's the ChatGPT's response. And there clearly is a kind of shock to the statistical community regarding what we should do. So this paper actually is a very interesting one. I would encourage you to read it if you are into the kind of the ecosystem of the data science and AI. So this author is a famous statistician, and his main point is that the primary reason is because of what he calls the frictionless reproducibility, FR. It is because the AI community has created so many opportunities for doing the following things: data sharing, code sharing, and competitive challenges. So all the algorithms are tested on the data, and all the code are shared, and people can test them. So this has contributed to the success of the current AI explosion. And I think his next point is to say that many different disciplines, I believe, including environmental health statistics, can benefit from such a model. Clearly, the question I will mention later is, do we have data sharing? Do we have good code sharing? Are there any kind of benchmarking going on so we can know how well different algorithms are performing? I think this is some kind of philosophical view that I want to share. And also a point for discussion, are there any barriers for preventing data sharing, code sharing, and doing some benchmarking? So what are some low-hanging fruits? So I was primarily thinking data and code products. I was looking at the National Academy of Science review or brief, that's what they call it. So there are people suggesting that we can do systematic reviews of research topics using large language model. That sounds reasonable. I haven't done one, but it's not surprising that people are using that tool. Second is that data product documentation and data dictionary. So this actually came up during one of Biostatistics faculty retreat. So our question, actually I was posing a question to the faculty in Biostat, what can we do to use the large language model to help with data analyses, regardless what step it is: pre-processing, documentation, analyses, presentation, interpretation. So many faculty actually sort of voted for. We do have a voting process to show which is the most popular idea. Many people wanted to have their data, to have good documentation. They were wondering, can we create these documentation using ChatGPT, maybe tuned to local data, maybe tuned using knowledge graphs, and also production code annotation. So, I have read many code from students, and I have seen them going from year 1 to year 5. And the code annotation basically goes from like unreadable to super good. I was pushing them to produce good code annotation. The question then is, can we have this kind of annotation using ChatGPT? For example, hey, this is raw code. Can you help me annotate this? Maybe you can provide them with the context in which these code are being produced. But I think this can potentially save a lot of efforts, time. And there are other use of these tools too. So I encourage you to think about it. Ethics considerations. First one. So I don't know whether EHS would need to train these large AI ML models, I think that the fine tuning or the adaptation to local data set is going to be the most is going to be the way to use these tools, but still kind of leverage our expertise in particular domain science. But indeed, if these models have been trained, they're producing lots of carbon footprint, and it has been an ethics consideration. The second one is about, propagating misinformation, especially in the area of climate change. So if somebody built an AI recommender and that's just going to spit out misinformation, that's going to be, very hard to correct. And there are bias issues, so this can come from many different reasons. If you have kind of a data that you just feed to the machine learning algorithm without considering how it's being collected, it could perpetuate the biases. For example, if the algorithm is recommending certain actions, if that certain action is not paying enough attention to certain subpopulations, it could lead to bad consequences. And there are fairness issues, and I'll talk about this. Ethics training, right? So we all, if you're a PI or co-I, you always have to do those peers certification so that you're going to have access to certain data. Actually, there are tools. You can just do a screenshot of the question, and then you can just complete those ethics training like in 5 minutes. But if you have done this, it's not going to take only 5 minutes. It's going to take you at least like 1 hour or 2. So if people are using this kind of tools in your research pipeline, what are the consequences? Especially if it's a field where the data privacy and data kind of ethics are very important. I asked this question to the vice president of IT in our university. I think his response basically is that you cannot control this. You have to I don't think he has good answers. But anyway, I just put it out here because it's related to the research team. And finally, reliability. So this is I think if you're working in computer vision, you know this very well. So please forgive me if I'm repeating this. The task is trying to reading the image and predict what's in the image, right? So the first row on the left is cow, and second row on the left is camel. And it turns out that there are many algorithms that's going to predict the image on the right to be a camel. And what's the reason? It's because the algorithm find, hey, the background is yellow or brown and must be a camel, right? So this is a potential issue that needs to be addressed because it's not learning the causal relationships of the image input and the labeling. So there are many people working this. The primary approach is to introduce a kind of a Bayesian network where there are a few nodes, the true object in there, the label, and also the background, right? So they're trying to let the machine learning method to understand there is a confounder that's called the background. So anyway, this has been an issue in computer vision. Not sure whether it has been an issue in the EHS context, but again, that's why people are talking about reliability and embedding causal models or DAGs into these kind of tasks. So what are the barriers and action items? Again, I was borrowing a lot of wisdom from the report. There are questions about data quality, and second, how can we, mimic the success of current wave of AI methods to use data sharing to, have more people try out on the data and produce better performance. And the third thing is that when we publish a paper, the most detailed information is in table 1 and summary, right? What's the process that we get to arrive at that point? We have the data. And that's usually lost. You've got to talk to the person who actually has written the paper, who has guided the study. So this data provenance or processing of data, that should be somewhere, but it's often not there. So are there incentives for people to do this? I'm not sure. And fourth thing, which is important, is how we communicate these complicated model results to the community who are consuming these results, the stakeholders and funders. And fifth, I believe this has been touched on as Moore's talk, but there's a balance between interpretability and predictability. I'll not go into this. And finally, on the training, do we want our trainees to have trainings in computation, in AI? I think the fact that we're having the symposium means yes. But how do we do this? I think that either takes the form of like a joint degree or some regular workshops. And usually I really like, at least my students, to have like pie-shaped talents, right? One in computational methodological area, deep, and the other in substantive area. It's not enough at this age to have a T-shaped talent where you're just deep in one. This may be controversial, but at least in my view, to do good science, computational science, you have to have pie-shaped talents. I probably will have to, how much time do I have? Zero? Okay. Anyway, I'm going to say that AI and statistics are really co-evolving and can really address a lot of important questions. And my view is that as a statistician, I benefit greatly from my colleagues who can pose important scientific questions. And that's why we can be kept relevant, right? I don't want to work on a problem that nobody cares. And we do have some strength, a great deal of it, in terms of design, methods, causality, required probabilistic assumptions, and lots of computational tool. Clearly, we need to adapt to it. Maybe wear the t-shirts as AI, and then just start talking to people. So we need to have those augmented AI expertise. And I believe we're a lot of fun. So that's usually when good work are produced. So I encourage you to reach out to Biostat faculty and trainees for future work. And I think that's all my talk.
It's a very great topic and all the thoughts. So to save the time, we'll save all the questions for to the end for discussion. So we can let the next two speakers to present first. Let me go to the next one. There you go. So our next speaker is Dr. Liyue Shen. Liyue actually just joined the University of Michigan last year, but she's already a rising star. So she graduated from Stanford with a EE as a major. And she also has been a postdoc fellow at the Department of Biomedical Informatics at Harvard Medical School. She is a recipient of Stanford BioX both graduate school student fellowship for 3 years in a row, and was selected as the rising star in EECS by MIT, and the rising star in data science by the University of Chicago in 2021. So it's not me calling rising star. So it's really by the words. So her research interest is in biomedical AI, which lies in the interdisciplinary areas of machine learning, computer vision, signal and image processing, medical image analysis, biomedical image, and data science. She is particularly interested in developing efficient and reliable AI and machine learning driven computational methods for imaging and informatics to tackle real-world biomedicine and healthcare problems that include but not limited to personalized cancer treatment and precision medicine. So today, she is going to share her research on prior-informed AI for medical imaging. So thank you for joining us. So welcome.
Yeah, thank you so much for the kind introduction. So as mentioned, my research is mostly what we call the biomedical AI. I came here today very happy to also know about what is the environmental health and also what is the important problem in the public health. I will provide something we have been talking or researching on in the biomedical AI for the different important problems, and especially what kind of solution we provided that's relevant to the AI or machine learning. I hope to see if there is any overlap or any potential collaboration opportunity that we can use or extend our AI or machine learning algorithms to solve your problems in the public health or in the environmental health. So that is my key motivation today. And I will include some like the specific technical part. Hopefully that's not very too complicated to understand. But if there is anything that is very specific or like, too hard to understand, feel free to interrupt me. I will try my best to explain it in a good way. Okay, so let's get started. And so firstly, as we can see, like how AI has been changed in different things in our life, like including the self-driving car and also the ChatGPT. Since the end of the last year, well, people may have been used every day by using this as some like the tool. And this is also relevant to some like we call the general AI or generative AI. And especially for the previous application I have been caring a lot about is the applications for the biomedicine and healthcare. So since this kind of paper published on Nature in 2016 about the skin image classification, where the first convolutional neural network has been developed on the large-scale skin images to finish the classification task for this specific problem. And there we have been seeing a lot of like different applications in this domain, including the segmentation task, which has been very important for different clinical protocol, like for the cancer treatment or other things like this in the CT or MRI. And we have also seen the applications, for example, to predict the protein structure. That is what the AlphaFold is doing by OpenAI. So we have really seen quite a lot of different applications in these areas, what we call the biomedical AI. And this also has become a very quickly expanding areas for both the industry and also the academia research. For example, the different tech companies, they have contributed and also invested different amount of like the applications and also the investment in this different in these areas. And also for the academia, we can also see like a lot of interesting research works are ongoing and with the different like different modalities or different disease. So this is what we have seen over the past several years, how this field is going pretty fast and rapidly. And this also comes to the key motivation for my research over my PhD and also for my future career here as well. So what I really want to understand is that how can we use AI or machine learning to understand the human health at the different levels. So for example, in the human level, we have seen like, okay, people may have some like the depth sensor or the camera in the hospital that could better understand or monitor the actions or behavior of doctors or patients. And this may be helpful to improve the healthcare, like regarding to promote efficiency or to remove the redundancy, for example. We have also seen like how AI can be useful to help with the doctor's job, like when we're looking into the internal structures for the human subjects and like through the CT imaging or MRI imaging, how can we use the AI tool to help to analyze the image data, and that could be help with the different downstream tasks, including the disease diagnosis or improve the personalized treatment. And moreover, we can also see like how AI can help with the scientific discovery and also different applications, for example, to help with like the understand how the coronavirus is behaving under the microscopic image, like in the real time. So these are all the things that is very important applications we have seen so far for the different domains for relevant to the healthcare and biomedicine. And from the other perspective, like in order to make the AI machine learning can be helpful for these different applications, how specifically or what kind of stages it can be useful. So I would like to see this as the different stages, including the imaging and the processing. So since I have been mainly dealing with the imaging modality, so first we want to understand is that how can we obtain or how can we get to the imaging from the different cases or from the different devices or sensors. And then the second part is that after we get the image data, how can we understand it? How can we extract the useful information from the different image modality or different data modality for the biomedical applications? And then finally, how can we deploy this in the real world clinical protocol to make this can be really impactful and useful to help with like doctors or the other clinical procedures? So these are the main things how I consider the research areas in the biomedical AI and also the different fields I have trying to and will continue try my best to contribute to in both the potential impact in the methodology for the AI machine learning development and also the applications for different biomedical domains. So this is some like the overall scope about the research areas I have seen so far. And then I will give some specific examples in the different stages or the different protocols regarding this kind of the overall pictures to give you some real sense like, okay, how exactly this can be helpful for the different applications. So I will mainly talk about in these two parts, as I just mentioned. The first one is that how can AI be helpful for the biomedical imaging? So again, this is regarding like how can we obtain or recover or get the imaging data in the different cases. And the second part is that after we get the image data, how can we process the data to get the important or useful information from the different modalities? So that will be the two main parts I will try to cover, and also at least in the high level in this talk. And for example, after we have introduced the AI or machine learning in the different application domain, and there are also some challenges that come along with at the same time. For example, the reliability for the AI model or the generalization. And what does it mean, really? So for example, if we consider for the different AI models, how can we leverage the different population priors to help us develop more reliable AI models? So this is what we call the population prior. For example, if we consider the doctor is trying to give the diagnosis or trying to get the specific outcomes predictions for the specific new patient, and the doctors may use their previous experience about the other patients or the large population cohort to help with that. So this is what we call the population prior. And the second thing, the specific protocol, such as in the personalized treatment, we care about the patient-specific scenarios where we want to use like the temporal sequential images for the specific patient that could be helpful for like the future prediction or like the personalized or the individualized treatment for the specific patient. And furthermore, we also know some like the medical physics from the different imaging scanner, which is not from the data-driven process, but if we could incorporate this kind of the medical physics prior knowledge from the imaging systems in the development of the AI model. So this is what we call the prior informed machine learning. So in order to address the challenges we have facing so far about the medical AI models regarding like the reliability or generalization or data efficiency, we want to propose more reliable or trustworthy machine learning or AI model that could incorporate the useful prior knowledge to further boost or to improve the robustness and also reliability for the AI models. So this comes to mostly from the methodology side, like what kind of the specific contribution we're doing for the medical AI development. So which means that instead of just the get like the off-the-shelf models, like what people have been using for the natural image for the different medical data, we're trying to think in specifically what kind of the model that we should exactly develop for the needs or for the requirements for the biomedical data specifically. So that comes to the main contribution and also logic through the different projects in my research. So to give some specific examples, and hopefully there could be some like similarity or correlation with the problems in the environmental health. So the first thing that we're trying to solve is the general inverse problem in the medical imaging. So for example, we know for the CT imaging, the patients will be exposed to the radiation exposure. And if we could do the sparse sampling for the CT reconstruction, that could be helpful to reduce the radiation exposure for the CT scanning process. So this can be formulated as an inverse problem for the medical imaging, and also similar for the MRI reconstruction. How can we use like smart sampling in the case space to reconstruct the high quality MRI images? So this is what kind of the important problem we're facing for the medical imaging domain. And in order to solve this kind of problems, we're trying to leverage the population priors that is captured by this new generative AI model called the generative diffusion models to incorporate the population prior or from the data distributions to solve the in general inverse problem. So there may be like too many technical details here, but I want to emphasize a little more in the high level insights. So how can we capture the data distribution prior or the population priors that we are trying to incorporate as one kind of the prior knowledge from the different population cohorts, for example, from the different patients. So in order to do this, I may want to introduce briefly about what is the generative model. So just to understand really from the very high level, so the generative diffusion models is trying to gauge or trying to train this kind of the generative modeling, which is capturing the underlying data distributions through the generative or sampling process. So when we are trying to develop this model, we trying to learn the mapping function from the pure noise Gaussian noise distribution as shown on the right hand, and then to connect this with the real data distributions in the real image data or the other kind of the data format. And in this kind of way, when we are sampling some like the noise sample from the Gaussian prior, and we could be able to generate the clean data that belong to the underlying distribution. So this kind of methodology is introduced as the generative modeling for the natural images. But actually, it can also work for the medical images. And in this case, what we are capturing is the data distribution, or in the other words, is the population prior across the different patient cohorts. So for example, if you provide the lung CT images as shown in this example across the different patients from some institution or some hospital. So what we are trying to capturing here is the population prior based on the distributions of the lung CT images across the different patients in this institute. And this is how we capture the data distribution prior and trying to use it to solve the inverse problem for the new patients that were coming like for the next visit. And in order to do this, the key point is trying to formulate this using like the Bayesian rule, and also to solve the inverse problem by considering this kind of posterior score functions on the data distribution. So here we will have we can decompose this kind of posterior sampling or posterior generation as two parts. One part is the score function for the unconditional data distribution. So this is actually what has been captured by the training of the diffusion models or generative diffusion models here. And the second part is the for the process. So what is the probability of the y? The y is the measurements here, then giving the data. And by combining these two parts, we can be able to get the posterior score function that will be helpful to solve the inverse problem. So to give a more concrete example, like in the CT or MRI reconstruction, so the measurements here is the raw data or the measurements data that we obtained from the CT or MRI imaging scanner. And in this case, that will be like the radiant transform or the sinogram for the CT imaging or the K-space for the Fourier space data for the MRI. And in order to combine this kind of the measurements data and also to solve the inverse problem, we'll propose this kind of the conditional sampling process with the that can be able to incorporate the population prior that is captured by the diffusion models showing as the red box here, which is denoted as the PX, and also the measurements from the observation that is the Y can be injected into the sampling or generation process. So that will be able to incorporate the information from both sides that can be generate the results of the PX giving Y, which is actually the posterior sampling or posterior distributions we want to obtain to solve the problem. And hopefully this is not too many details to understand it, but I just want to show some examples how it could work. So by using this kind of the general methodology, we will be able to solve the inverse problem for the CT reconstruction and MRI reconstruction pretty efficiently. And especially it can be very flexible to adapt it to like the different anatomical size or different imaging modality or different sampling pattern. So this is because like we are using the unsupervised training mechanisms for the data or for the training process that can be able to capture the data distributions in order to do what the previous deep learning-based methodology are doing for the image reconstruction. And I just get to know this from the launch, like the people here may also care about the satellite image applications, which is also another application field we're working on and also be relevant to the generative diffusion models as well. So in this kind of case, we're trying to do the sampling or generation for the satellite images that could enable the association or to connect or to incorporate the metadata from the satellite image, such like the geolocation as a conditional information. So for example, you can see here the metadata that will be the different time points or different latitudes or longitudes. And especially, for example, in the environmental health, I can imagine the conditional information can also be like the disease or percentage or for this population cohort or in this kind of specific location. So this can also be able to capture some like association in the semantic domain regarding for the conditional information and also the generated images like for the satellite image as well. And here is some examples that showing like how this kind of the metadata or conditional information, but definitely this paper is about the geolocation. But if we could combine this with like the population health or public health information information as the metadata. So this is something we are also working in one of our ongoing projects. But in this one, we are not looking to the health information, but more about like the, for example, the forest information or the agriculture information in these specific locations, where we're trying to generate the satellite images. But I can see like this may be some potential interesting applications that to combine with the public health as well, or the environmental health. Yeah, so that is the first part about the genetic diffusion model. And beyond that, we're also dealing with about the personalized treatment that will specifically can be able to handle the long sequential or the time series data in the medical images. So for example, we're considering the patients which is under the treatment, for example, in the radiation therapy, there may be like multiple visits or multiple fractions for the radiation treatment for the same patient. So in this case, what we are caring about is actually the temporal relationship for the sequential time series data. So in this kind of the line of the project, we care about the personalized model or the individual treatment, and we propose some like specific machine learning model called the implicit neural representation learning that could be able to capture the spatial temporal representations for the longitudinal study. So this could also be some like interesting applications regarding for this kind of the AI methodology, as what Dr. Wu mentioned in his presentations for the spatial temporal study in this case. And there we're also applying this for the different clinical applications that is specifically relevant to the radiation therapy under the cancer center, and especially what they are calling what they are caring about for like the motion tracking, the longitudinal study, and also the super solution in their specific clinical procedure. So hopefully this could also be something, potential applications that will be interesting for the environmental health in this application domain. And the last things I want to mention is about the physics-informed learning. So as we just mentioned, there may, if we just develop the AI model through a pure data-driven way, there may be some like very obvious shortcoming or some like the challenges or concerns from the people about the reliability. So in this kind of physics-informed learning, we're trying to incorporate the physics priors with the data-driven approach to deal with the different problems, including the medical images, what I have mentioned so far, and also our recent collaborations with the faculty in the physics department about the physics-informed score-based generative models for the inverse design of the quantum photonics. So in this kind of way, we're trying to incorporate the physics knowledge to give this kind of predict the relationship or the function from the photonics structure device structures with the corresponding desired physical properties that we want to achieve, and also using the genetic diffusion model as a way to capture the here we're capturing the distributions across the different devices regarding the different patterns they have in order to conduct the inverse design for what kind of specific structures we can design in order to achieve the desired physical properties what they want to get. So this can also be one of the specific examples to showing the potential expansion of this kind of AI methodology, which is not exactly limited by the medical applications, but very in general for the different scientific disciplinaries and also the applications. So that will be the first part about how can we leverage AI for the biomedical imaging, or in general, like more on like the scientific inverse problem solving in the different application domain. And the second part is more about how can we process the data. So in this kind of way, what I'm mostly working on for now, the first part is about the multimodal learning. So as we can see, like for the biomedical applications, there are a lot of like different modalities. So previously, I'm mostly caring about the imaging modality or different imaging modalities, but there are also many important informations from the other modality. For example, in the radiology reports, in the EHR, the electronic health records, as we have seen in the talks this morning, and also in the genomics, and also the pathology. So we have trying to provide a general guidance. How can we efficiently fuse or combine the information from the different biomedical modalities that could help with the personalized treatment or prediction for the specific individual for the patient. And for example, for the current ongoing works, we're working with the different modalities, including the X-ray images and also the medical reports, and also for some collaboration with the faculty in the biomedical engineering, we're trying to investigate the association between the brain signal and also the body signal, like the functional MRI and also the cardio or respiration signals from the EKG or ECG. And we're also looking into something relevant to the genomics data. So I think that will be also maybe interested for the collaboration in this community, where we are trying to investigate the fusion between the pathology images and also the genomics data. And I know, like with the support from the Precision Health program at they actually provide a very large scale of the data for the EHR. And I hope there could be some way to incorporate also the modality of the EHR in our multimodal learning framework. And in that way, we definitely want to collaborate with some specific experts in this domain for the EHR or for the genomics. And the other way that we are also very caring about is to solve the data efficient problems in the biomedical domain. So, for example, if we want to train some like the biomedical AI model, no matter for the single modality or multimodality, the data collection and the labeling is always a bottleneck. So the other directions we're trying to investigate more is about what we call the self-specific learning. So which means that with a limited number of the data or annotations, how can we get the efficient, or how can we train the efficient AI models from this kind of the limitation? And the specific example, like the segmentation task, right? So if we want to do the segmentation or to predict the segmentation labels for a sequential of the medical images, or like the 4D MRI or 4D CT, or like some patient with a sequential visit imaging from the different scanning different time points. So if we can provide the segmentation labels at the first frame or at the first visit, how can we do the prediction for all the following up frames, or in this video data, or in this kind of time series data? So this is what we have been investigating through the self-supervised learning, and the specific model that we're using here is the prompt-based segmentation model. So I will not get into too many of the details, but this is also something we're trying to address the data or the annotation limitations for the biomedical applications in this domain. And finally, with the investigation or research further in the multimodal learning and also the self-supervised learning, our goal for the final achievement is trying to get closer to what we call the generative medical AI framework, which means that it will be possible to have like the multimodality as the input or as the output, and through the interactive way to use the AI tool to help with the different procedures or different clinical protocols in the different applications. But this is definitely something we're trying to foresee based on the multimodal foundation models, but it's not really something that we have achieved so far, and we're definitely on the way there, but I still think like it's promising to go step by step and get closer and closer to this kind of generative medical AI. And in order to achieve there are also some like important problems we need to address to train or develop the multimodal foundation models. So for example, in order to develop the foundation models like what we have seen for the GPT models, we definitely need tons and also the very huge scale of the training data. But as mentioned earlier, this is not very feasible for the medical applications. So one thing that we are investigating in this line is trying to see like if we can use the predictive learning to develop or to scale up the training of the multimodal foundation model, especially to overcome this kind of bottleneck by leverage or by decentralize the training in the across the different centers. And in this way, one of the important problems is about the data heterogeneity. Like the different hospital, different centers, they may have like different population distributions for their patients cohorts. So how can we make sure this kind of decentralized training performance can be as good as the centralized training? And this is some important problems we're trying to investigate, especially under the setting for the multimodal learning. And the second thing is that how can we promote or guarantee the fairness and also the privacy protection for the medical AI models in general? So for example, we have already seen some like the challenges and also concerns about the privacy leakage from this kind of the AI model that has been trained on the different training data. So how can we avoid this kind of the leakage for the sensitive privacy patient information to guarantee the fairness and also the privacy preserving model development in this kind of the pathway? So this is also some important problems we are trying to investigate and also to ensure the fairness and also the unbiased model development for the medical AI. So these are something that I want to share at the different examples in the different directions for the medical AI research. And in general, I'm working in this kind of intersections between the AI machine learning field and also the biomedical applications. I hope my research could contribute and also show the impact in both the methodology and also the and also the application. So this is also the motivation I want to reach out and also have this kind of the opportunities to talk with the different community and trying to see like what kind of the problem is important in your domain and what kind of solutions that I could provide to help solve your important problems. Yeah, so that is all the things I want to share today. And there is my email contact. So if there is any questions or if there is any interesting thoughts to follow up on any of the projects I have talking about, feel free to reach out to me. I'm very happy to follow up. Thank you so much.
Thank you. Excellent talk. So again, we'll save all the questions toward the end. We actually have the rooms reserved until 3, so we will open the floor for discussion after the next talk. So next we'll have Professor Qing Qu from the Department of EE and Computer Science again. And he is also affiliated with MIDAS, as well as the Michigan Center for Applied and Interdisciplinary Mathematics and the Michigan Institute for Computational Discovery and Engineering. Qing received his bachelor degree from Tsinghua University in 2011 and obtained his PhD from Columbia University in 2018. So Professor Chu's work has been recognized by many prestigious awards, including a Microsoft PhD fellowship in machine learning, a NSF Career Award in 2022, and an Amazon AWS AI Award in 2023. His research interest lies in the intersection of signal processing, data science, machine learning, and numerical optimization. He is interested in how to leverage the tools from machine learning, numerical optimization, and high-dimensional geometry with applications in imaging sciences and scientific discovery. So today, he's going to talk about exploring the low-dimensionality for more robust, efficient, and explainable AI. So welcome, Dr. Chu. The floor is yours.
Thanks for the introduction. My name is Qing. I'm a current assistant for ECE. So my research mostly focuses on the methodology side of machine learning, but I'm also very interested in how to apply those tools to scientific disciplines. So first, I want to start with a broad overview. So in the past, I think 1-2 decades, right? So we have witnessed tremendous success, especially the success of deep learning is that starting from, I think majorly from 2012. So the ARLEC-NET will receive a significant improvement compared to classical methods in terms of accuracy. And in the past 1 decade, right, deep learning has transformed many fields like computer vision, natural language processing, protein modeling, healthcare, etc. that Liyue has discussed. And nowadays, people are building larger and larger machine learning models, right? From ARLEC-NET, where we have maybe 1 million parameters, and then we are increasing to ResNet, vision transformer, and mixture expert models. And for language models, right, we have this kind of ChatGPT models, right? They can have trillions of parameters. And what you can observe and what people believe nowadays is that if you're building larger models, you get better performance, right? And this is indeed the case, is that you're increasing the number of parameters and the model is getting performing better. And if you look at ChatGPT on language models, right? So it almost becomes a zero-shot learner, right? You can, once you train the model, right, it can adapt to any task without any fine-tuning or training. But however, building larger models has certain limitations, right? We cannot always, I mean, this game is not sustainable, right? If you're building larger and larger models. I think there are several challenges. So first, the challenge is that if you're building larger and larger models, right, you need more and more computation resources, right? The cost of the computation is growing exponentially with respect to the dimension. And second challenge is interpretation or explainability, but how can we trust those models, right? So if the model is so large, it's a black box model, how can we trust what the model produced, right? So nowadays people are talking about this kind of hallucination issues and the privacy issues of this large language model, but how can we trust and interpret what those models doing? A third issue is that those models are actually not that robust. So say if your models, the data, I mean, if you consider supersetting, right, when you train the models, and there could be some like say label corruptions, or you have some adversarial attack on your data, right? The model will come up totally wrong output. So the question isn't the computation, the interpretability, and the robustness of these models, and how can we address those challenges when we're building those large models. And this is something that I'm thinking about. So I think to deal with those challenges, right? So although we are like building models with larger and larger dimension, I think the larger dimension obviously creates some benefits. Like if you map your data into higher dimension, it's easier to discriminate your data. But the larger model actually, the intrinsic dimension of the models could be still very low, and there could be a lot of redundancies in the model parameters. That could lead the benefits or the potential promises of reducing the computation cost, improving the interpretability, and to deal with robustness of those models. And this will trace back to many tools that we have built in statistics, in optimization, and in signal processing. Is that traditional tools is that we are analyzing, providing statistic optimization guarantees. Is that the model or the data itself often has low-dimensional structures, right? And that's the way that we can guarantee our model works with finite training samples, right? For example, your data itself could be low rank, and there could be sparsity pattern in your data and models. And this is about the figure I'm showing here is basically about the data. But I think if you are building larger models, right, the model parameters itself could have low rank and this kind of low-dimensional structures within the data, such that within the model, such that even you are building larger models, because the intrinsic dimension is still low, you don't overfit to the training data itself. And this is the underlying promises. And actually, in the past 5 years, researchers in the field are starting to realize these key connections between low dimensionality of the model and data, and they try to build a white box machine like deep network architectures. They try to understand representations of our machine learning models from this kind of low dimensional perspective. But basically, the models are doing this kind of subspace clustering in terms of last layer, and they're trying to understand the generalization performances, why this kind of double descent generalization phenomenon happens of more than over-parameterized neural networks. So here I want to provide 2 examples I'm working on, that how can we leverage this kind of a structure in the data and the weights to provide efficiency
unmute. And
So glad,
I don't know, I think. Hopefully that means we're, oh, screen sharing,
Yeah.
of course. I'm sorry, you're this one?
Yeah.
Oh, no, actually,
PDF.
I think.
this
Yeah.
one probably.
Great.
And then what, Control L is full screen?
Yeah.
Or, oh, hang on,
Yeah, you would click on it and then.
So that-
this one?
Yeah. There we go.
Okay, we good?
Sorry about that.
Anything here? Yes, so the first example I want to give is about how can we improve the efficiency of like training large models. So the modern machine learning pipeline is following, right? So especially you think of this ChatGPT and this large language model thing, is that firstly, we train the model on a large amount of training data set. We train a very large model. And then if you consider a specific task, like for example, the environmental health applications, you will fine tune your model on a specific data set. And then you do the inference on the specific task in environmental health. So this is the first step is pre-training. So usually, for example, you train ChatGPT 3, right? It has like over 100 billion parameters, and it will cost roughly like 350 GPU years to train such a large model, right? It's really expensive. And now the ChatGPT 4 is rumored to have like 1.8 trillion parameters. And I don't know how long it needs to train like such models, right? It could be extremely expensive to train such models. And there's someone predict that in the next 3 years, the shortage is not the GPU. Actually, the shortage will be the power to train those models. So, but unfortunately, this needs only to be done once. But still, it's very expensive. And the thing is that we find recently is that if you look at the waste of the models we are training nowadays, right? So if you think of W naught, it's your initialization of the weights. And this delta W is that you train the weights using gradient descent to update the weights. And if you do a singular value decomposition of the weights in the later layers, and you plot the singular values, right, you can see that actually the weight update is actually pretty low rank, right? The majority of singular values actually is concentrated on like a very small set of the indices. And moreover, if you sort the indices, right, and this x-axis is the sorted singular values, and right this y-axis is denoting the number of iterations. And what you can see that actually the update is only happening within the same subspace of the weights, right? So, and the weight is low rank, and it's invariant across a number of iterations. So which means that actually you can do, potentially do model compression, right? You can compress the model into a smaller dimension, and then you can consider accelerating the training of such large models because the intrinsic dimension could be very small. And indeed, we test this idea on some like simple settings, right? So we consider like a very simple setting, and we do this kind of a low rank weight compression. And actually, the thing we find is quite promising is that the compressed weight exactly follows the original learning dynamics, but the training time can be significantly reduced. And this could potentially save the memory cost as well, right? Because if your weight is low rank, then you do this kind of low rank factorization, then the number of parameters you need could be significantly reduced. And this is about model pre-training. So another, the second step when you pre-train those models, right? So you need to fine-tune the model to specific tasks, like for example, for environmental health, and then you need to fine-tune your pre-trained model for specific data set to get a better performance. And so fine-tuning is basically trying to specify your model to the specific downstream tasks, right? And a popular approach nowadays for fine-tuning, especially when after the ChatGPT boom, is this idea of a low-rank adaptation, and this is the methods that are applied to large language model and ChatGPT. It's become very popular in the last 1-2 years. And the basic idea of fine-tuning those models is that CWPT is your pre-trained model. Right? This is after pre-training. And if you want to fine-tune your model to the specific task, is that you are adding extra factorization, and this W2 and W1 are low rank, where the intrinsic rank is R, right? R is much smaller than the ambient dimension. And the reason people do this low rank factorization is because for large language models, usually the model are transformer based, and all the weights actually are matrices, right? And what you do is basically you add a low rank factorization and fine tune the model. And after you update this kind of low rank factorization, the fine tuned model weights will be this WFT, right? And this weights W2 and W1 will be updated through gradient descent on your downstream path.
So do we need new data to do this?
Yes, you fine tune on the downstream data set, and the pre-trained model is frozen. You don't move the pre-trained model, and you only update W2 and W1 because R is very small. So the number of parameters you update is significantly smaller than the pre-trained weight. And this is called low-rank adaptation, or LoRa. It's become very popular in the last 2 years. However, LoRa is very effective, but sometimes choosing the hyperparameters, for example, the rank R, could be kind of non-trivial. And how to choose this rank, especially when you have very limited downstream data, choosing a very large rank R could lead to overfitting issues on the downstream task. And in our recent work, we try to deal with this kind of overfitting using LoRa by resorting this to matrix factor, low rank matrix recovery problem. Is that if you think that this phi, which is the difference between pre-trained weights and fine-tuned weights, as a low rank matrix, right? You can cast this as low rank factorization, and you can use multi-layer like weights to approximate the low rank matrix. And recently people find is that if you're using multiple layer factorization, actually the depths can help you to prevent overfitting, right? This is a case where L equal to 3. This blue curve shows you the generalization performance when L equal to 3. And this is the curve showing you the result showing you when L equal to 2. And you can see that using 2-layer network will overfit, but using 3-layer doesn't overfit, even you increasing the number of parameters. And also increasing the Ys can reduce the number of iterations to convergence. And we use this idea to modify LoRa. And so what we find is that if you apply like a LoRa with layer equal to 3 and R equal to D, you will see that the end-to-end matrix actually is very low rank. So the singular values will concentrate on very small number of indices. And if you compare the conversion weight subspace with all the learning dynamics, and you can see that actually after a certain burn-in period, the subspace doesn't change anymore, but it stays within the same invariant low rank subspace. It doesn't like move, it will stay invariant across the number of iterations. Even your training loss is decreasing. So based on this, we introduced this idea of called deep LoRa, is that we're using several layers, 3-layer factorization instead of 2-layer factorization. And what we find is that our approach is performing better when we have fewer number, especially when we have limited downstream samples. And this is a very valuable because for many applications, the training data points on downstream tasks is very limited. And our approach actually getting better, performing better when we have limited fine-tuning samples. And also, if you look at our performance of our approach versus the rank, but you can see that our approach is performing quite robust across a number of ranks and doesn't overfit. But if you use LoRa, right, LoRa will overfit when you're increasing the rank of this kind of fine-tuning hyperparameters. And moreover, we also plot the rank of the updated weights, and you can see that actually LoRa, I mean here, LoRa is using rank equal to 8 factorization, right? It always stays the rank 8 factorization for each layer, but using our deep LoRa, actually we can adapt to the intrinsic rank of the problem, right? So you can see that a majority of the weights update actually is the rank 0. It doesn't update at all. And then there are several layers where we'll update the weights, and we can adaptively choose the rank to prevent overfitting. So the second topic example I want to give you is that, so if you know that there's an intrinsic dimensionality in your model, right, you can utilize to accelerate training efficiency and fine-tuning efficiency. And another aspect I want to present you is that you can also utilize this idea to improve the robustness of your models, right? To make your model more robust. See, when you are training your models that with many like label noise on your training data set, and how can we use this kind of idea of identifying the low-dimensional structures in your data to make your models more robust to corruptions and noises. So we know that actually there's a lot of observations in the past several years is that this over-parameterized models actually is not very robust. They actually lack robustness. So this is one of the examples that you'll find is that if you're making your training data, increasing the label corruptions of your training data, so the test error actually will getting worse and worse for over-parameterized models, right? So actually the over-parameterized model will be very vulnerable to the label corruptions on your training data in the supervised setting. And more recently, people also find that over-parameterized machine learning models are also vulnerable to adversarial attacks. And this is an example, right? So if you given like a panda, like this example to your deep learning models, right? It has like a fairly like a say 60 confidence that this is a panda. But if you add small noise perturbation, and our human eyes can still recognize this as a panda, but the machine learning model actually is very vulnerable to this kind of small adversarial attacks, that they will recognize this as like a bond with like 99% of accuracy, right? So actually the machine learning models we are building now is not very robust to this kind of whether label noise corruptions or this kind of input corruptions on your data. And the question is, how can we make the models robust? And so we propose an approach actually to model the noise and realizing the low-dimensional structures in your data and the noise to improve the robustness of our machine learning models. And here I want to give you a very high-level idea of how do we do this. And here first I want to show you that see if you train your machine learning models on noisy labels. So you see if you're consider a supervised classification problem that your training data is corrupted, your label are corrupted. And in those settings, so if you train your model until convergence, and if you see this bold curve, this is your training accuracy, right? You can see that the training accuracy reaches 100%. But your test accuracy, actually, when you train until convergence, you will exhibit overfitting issues because your training actually is basically memorization and this overfits to the wrong labels, such that the generalization performance will be decreasing. And we propose a new approach is that actually we prevent overfitting by realizing the low-dimensional structures in the noise and the data, that our training accuracy actually is only achieving like 60% because there's a 40% of corruption on the labels. And our test accuracy actually are getting very robust, and we don't overfit to to the wrong labels. And the basic idea and the high-level idea here is that we're realizing that the noisy label can be modeled as the prediction of our neural network, and the prediction could be pretty low rank, and the labels and the noisy labels or the corrupted labels actually pretty sparse in the training data set, right? And then we know that actually from classical robust PCA perspective, we know that actually low rank data and the sparse corruptions, they can be exactly separated to each other, right? And this is a key idea that how can we train our model to make them more robust, is that we are utilizing the deep neural network to fit into these kind of low rank structures, and then we add an extra model to model the sparse label noise, to separate the label noise from the correct training data. And our idea is, based on this idea, this is some technical details I want to just briefly go through, is that we consider this is our deep learning model, and this is actually an actual term to model the sparse label corruptions. And this is overall our training loss. And we just need to do a very simple modification of our methods to update both our models and to model the label corruptions in our data, such that the label corruption will be sparse. And by doing so, actually, we can make our model much more robust. And you can see that compare all the state-of-the-art methods, our method actually is performing much better with reduced time complexity, computation efficiency when we're training those models. And we also apply this idea for unsupervised image reconstruction tasks, right? So say if our image is corrupted by some sparse salt and pepper noise, and we can use deep network to recover the clean image and use this extra term to model the sparse corruptions in our data. And finally, I want to conclude is that here I give you two examples, right? If you're realizing there's structures, low-dimensional structures in the data and the models, right? You can improve the efficiency, improve the robustness of your models. But I think there could be a lot of things that can be done in the future. Is that how can we explore the structures in the model and the data to make them more robust, more interpretable, and more efficient. Thank you so much. Want to stop here.
So I'm going to invite all the speakers to here, maybe up here, maybe here. There is a light this way. So then we'll open the floor for discussions. Any questions for our speakers? Ta-da!
So I think my view is that there are lots of technical details, but I think the benefit is that you got to see how these models actually build and trained. And I think clearly, I want to make sure that these are the things on the hook that you may or may not encounter during your own, model building exercise. But these are like extremely important ways to say robustify the training, integrate all the data modalities. So I think my view is that in your next stage of career, if you encounter these type of data, I think these will be good references, or at least you know who to look for to collaborate. So I just want to sort of put a kind of note to the presentations.
Great talks. Really enjoyed it. Part of my job at Cedars-Sinai is trying to keep track of all the AI activities across our institution. I serve on our AI council, and I'm doing a survey right now of all the AI publications and which ones are possibly moving into the clinic. And it's a big task, and we're a much smaller place than the University of Michigan. So I guess my question is, how do you keep track of all the AI activity across the university, given how big the University of Michigan is? Seems like it's a very daunting task to first of all, just know who's working on AI, what are the AI innovations that are coming out of the university that nobody else has access to? How can you take advantage of those? I was just curious if you have any thoughts about the AI landscape at Michigan and how you're approaching it.
Yeah,
I think the issue that it helps because it's kind of minus activity.
yeah.
And also I'm crediting on CE and then a lot of workshops. Actually, we have a scientific foundation model workshop coming up in April. And that's the very important model of future technology. Yeah, definitely, I agree that there's so many papers on knowledge. It's very hard to keep track. It's very hard to keep track of the trend. And yeah, so I also often rely on my students to become papers to read. Yeah, it's really difficult.
Well, that's a related question. How do you keep track of all the AI that's coming out around the world? That's a much bigger problem.
Yeah, I think sometimes I rely on Google Scholar and sometimes I rely on Twitter to see that people tweeting there's a famous Twitter called AK, actually, they tweet a lot of these things, a very interesting model machine learning papers.
It's called AK.
Yeah. Actually, there's a rumor that AK recommends your paper. Like 99% they will get accepted into top conferences. I feel this is maybe not so healthy. I feel maybe you should restrict publishing so many papers, just focusing on publishing good papers, on high quality papers, rather than publishing so many papers.
You sure AK is not an AI?
I think so. If you have like a in-person meetup somewhere.
Yeah, I agree with what you mentioned. So I think regarding for the scope of this kind of different events, like including the symposium, this is exactly what we're doing, right? So I also have been invited for like different kinds of symposium and the different departments, and also sometimes they will have the workshop. We also organize the workshop with the support of Midas, especially on the generative education model. We're inviting the researchers around the US and also international from Korea as well for the topic we're especially familiar with, and to invite them to give a talk here and also to encourage discussion. So I agree, AI is pretty large and also very large scale, very large term, and I don't think anyone can keep track of all the events or the activities in different directions of AI, which means that including the CV, the NLP, and also robotics, all those things, right? So I think what I will try to keep track of is the specific direction I'm working on and what kind of the areas that was the most exciting and interesting to me. And even for this one, it's also very hard to keep track of the daily updates even. And we also have this kind of the reading group, among Qing's lab and also my lab and also another lab in our ECE department. And in this case, we are organizing the weekly gathering between the faculties and also the students in all of our group, and especially discussing the recent papers on the diffusion models. And this is what we are trying to keep track of the most of the recent papers and also what is very interesting to us. And definitely sometimes the students may even get quicker about the paper upon release on the archive than us. So we're also learning from each other. But in general, I think this is our efforts trying to keep track of the progress in these areas. But I would say even in this way, we definitely cannot do perfect or guarantee we know all the papers uploaded every day. But I think in general, it may not be really necessary to read through all the papers, but it will be more interesting to think about, from my point of view, what kind of the research questions we are trying to solve is important or valuable.
I don't believe I have a lot to add, but to Jason's specific question of how to organize the efforts within UM. So I know that the Precision Health Initiative, I believe, first established by the President's office. So the co-director is actually Brahmaji. So he basically would convene, say, ad hoc meeting, say, okay, you guys from ECE, you guys from Biostatistics, you guys from STAT, can you guys name a few people who would be interested in, say, seeing these large language model being implemented in clinical workflow. So actually, they are the easy part. I was part of the biostat part, so we had a meeting about 30 to 40 people, and the discussion basically involves, say, does Michigan want our own homegrown large language model? And I think there are different views, and I believe that it's good to have those kind of conversations. Some people say, "Hey, Stanford has it, University of Florida has it, so we won't have it because Michigan is so progressive." Or people say, "Hey, why do you waste as Qing was mentioning, like $50 million to train those big models? Why can we not just fine tune the existing models using maybe Michigan data, subject to the understanding that we do not want the data to leave Michigan?" Other things like MIDAS, actually at this right time and tomorrow, there is a workshop called AI in Science. But unfortunately, I don't see a lot of healthcare applications. So they're probably excluding healthcare from science, which I agree. So they have like physics, physicists, and other disciplines. So it's actually happening right now, tomorrow too. So I think that Midas, for the name of the bill, to anything he touches becomes gold. I think Michigan is really sort of capturing this trend, but what can we do about it? I think that's what we're going to see. I personally am taking like a large language model class, so hopefully we can learn more about details. Yeah, that's pretty much my experience.
This is relating to the whole concept of bias in the data. Do you think enough is being done, and if not, what can be done to ensure that relevant databases are used, accessed, and utilized for the pre-training data on some of these models? Is there anything more that needs to be done?
So you need to ensure the model training is not as biased as we see now.
Right.
I don't have a lot of experience there, but I guess we have to collect good quality data with good design and making sure we have data from most of the subgroups of people, so that the classification accuracies, or say the distribution of disease risk, are going to be comparable across different groups. Yeah, that's what people call like group parity. So yeah, that's.
Yeah, so if I understand the question clearly, you are asking like how can we guarantee all the fairness of the developed AI model for the different data applications? Yeah, so from my point of view, the bias could from the data, it also from the model. And yeah, regarding for the data, we're trying to reduce the bias when we are developing the model, but for some kind of the AI model, like the GPT, we actually do not know what kind of training data they are using to develop the model, right? And so it's very hard to say like this, what kind of bias they may introduce. And this is also what people concerns a lot. And in some of the ongoing work, as I know, there are some like the researchers trying to improve the fairness of the AI models, which means that they concerns not only the accuracy performance for prediction or what kind of the task, they're also considering the fairness or the equivalent performance across the different patient cohorts. So for example, if I read the classification on this patient cohort and also the other patient cohort from another hospital, can I guarantee they are achieving pretty comparable or no very divergent performance? So they are trying to propose the different metrics in their model development to ensure this kind of the comparable performance from the different population cohort. So I have seen this kind of the efforts people are trying to increase or promote the fairness, because this has become a concern, like more and more people are caring about and trying to avoid or mitigate. Yeah.
Yeah, I definitely think when I work on machine learning models, I feel definitely think that data actually is very important. Because now the machine learning models, if you look at the diffusion models, the generative models, and the large language model, what I believe is that the knowledge become very powerful, and they can actually learn underlying distribution pretty well. So I think if you look at across the say giving the same noise into the generative model and then generate the image, we often generate very similar images across different models. And I think that's the reason because all these kind of diffusion model are learning the same distribution of the data. So I think in that regard, the training data actually is very important. I think if you look at different models that different companies build, I think the difference might not be the model, but actually because of data they use is different. And that's my viewpoint. Maybe it's not correct, it's my conjecture.
So I also have a question. So I know like in your presentation, you showed many images. But in environmental health sciences, besides those images, most of the time we actually have time series like air pollution or some chemical exposures. So for those kind of data, and also our outcomes, not necessarily to be binary, to be disease, not disease, but we may have some health outcomes, continuous variables. For this situation, how, could you actually make some comments or guidance about AI or machine learning methods? Just have a brief introduction would be fine.
Yeah, I think this, so do you mean that the causal relationship between the
Well, not necessarily causal. It sometimes could be kind of association between some functions like curves over time versus outcomes. I would say like supervised learning or like unsupervised learning about clustering, like the Google has example for would be helpful, right?
Yeah, so I think the context perhaps is like a time series measurement of exposures to like thousands of chemicals, and maybe you have the outcomes that's monitored over time. Yeah, so I think to me that's indeed very classically time series analyses. I do see, again, I have not looked into this. There are people who are thinking that they're trying to do time series foundation model. Actually, I would ask the panelists here, what is foundation model? But people are trying to do these kind of general models that hopefully can be fine-tuned to, say, environmental health context. My guess is that if that can be done, we can just plug into Professor Moore's workflow and hopefully we can see the performance. And I think that serves as an ultimate judge of how good the method is. My question for you guys is, what is foundation model? And we heard so many kind of, mention a foundation model. What are they? I don't know.
I also feel like the models like you guys presented just now with those 2-dimensional image, if you reduce that to be 1-dimensional over time or over different location for air pollution will also work.
Yeah, exactly. So, let me answer the first question about time series data. So, I think that is definitely possible. So I can give an example about the diffusion model. So this can also work for the time series data. Like I have seen people working with audio signals and also the other tabular data, and also for the imputation problems. So for example, to complete the missing data, and what they're trying to do is that they're trying to learn the distribution prior from the giving like the time series data that used as the training part, and trying to use the completion or like predict the missing data through this kind of conditional sampling or conditional generation process. So I agree with what you mentioned. So the models we're providing here is not just limited to the images. We're also trying to investigate to the higher dimensional data, like for the 3D, because this is also very common for the CT and MRI in the real clinical practice. And also even the 4D data, and also for the 1D that is also similar. So this is not something, the data dimensionality, I don't think that will limit or constrain the model development. But there are also some like other possible solutions or model design for the time series data beyond the diffusion model. But this has become a very, very important, very interesting research directions people have been looking into. And to answer Dr. Yu's question, what is the foundation model? I agree, this is a very appealing, but very confusing term. And I will say this term is first proposed by the Stanford faculty since that paper, say for 1 year or 2 years ago. And I think what they are trying to emphasize is the generalization ability or the prior knowledge that could be embedded in this model. So which means that I can say like 2 key points from my point of view. The first one is the adaptation or the incorporation from the multimodal data. So which means that it's not very specific for the one modality, but it has the ability to understand or to reasoning across the different modality to incorporate informations regarding for the multimodal input or multimodal output. And the second one is the adaptation or generalization to the different applications. So which means that it has the potential ability or power needs to generalize or can work with the different applications. So which means that this is not an application specific model for the one like type of prediction, but the knowledge embedded in the model can be used for different applications in this domain or in this application. So that is my understanding for the what they call the foundation model. And this may also could be relevant about some people are trying to use for the pre-training fine-tuning scheme, which is I would say a very common paradigm for the foundation model development currently. So people are trying to use the self-spread learning for the data pre-training to learn the like the data relevant information or representations or embeddings from this kind of the which means that this kind of learning or association is not relevant to the specific task. And then they are trying to fine-tune the learned representations to the specific applications or specific tasks through the fine-tuning. So this is also one of those specific examples about the pre-training fine-tuning scheme, how people are trying to leverage this kind of, or trying to develop this kind of the, maybe can also call the foundation models in some sense.
Yeah, so you provide very like a general definition of foundation model. So in my view, I feel the foundation model often like they point to this kind of transformer-based data architecture models. I think in the transformer like kick off by this kind of self-attention is already neat paper in 2017 in East, and that's very become popular in language models. And then I think in 2020 or something, people make this work for vision tasks. They do this kind of vision transformer models. And then the transformer model can serve as like a foundation model that can work across multi models. They can work for languages, they can work for images, they can work for videos. And if you look at this kind of diffusion models, it's Sora, recently released by OpenAI. They are also building this on transformer-based network architecture to make this video generation work. Through the transformer, and also the transformer, they can the attention mechanism can capture the time dependent, long time dependent between different across time for time series data, and you can. And also, people argue that they have this kind of in contact learning capability that you put your data like as a prompt, and actually the next token predictions could be very powerful. Yes, that's my opinion. Yeah, narrow opinion.
Thank you. Yeah, it's fairly general. It seems like there's a struggle getting AI integrated into healthcare and actually finding where it's going to be applicable and how that's going to actually exist. Do any of you have any ideas of how you think that route is going to go? Do you think like IA is going to start being incorporated into clinical trials, or has it already, possibly? Just kind of an opinion-based question.
So that sounds like Professor Moore's question. But I think, I think that's a super important problem. And I will be organizing a session in a health policy conference, basically having people talk about this. So I'm still in the process of learning. I do see people publishing papers trying to use these generative AI tools to speed up clinical trials, be it looking within a big possible cohort who to recruit. But yeah, I think I haven't really implemented, this kind of things in AI tools in the healthcare workflow. I guess whoever can do it, he or she will be super influential. I think there are many people doing it for particular diseases, maybe for sepsis prediction. I think when people doing it, they can predict maybe 2 or 3 days before it actually happens. That's my experience.
It seems like it'd be really useful in the chronic disease management, long-term monitoring, cancer predisposition syndromes potentially.
Yeah, I think that's a dream.
Yeah.
Yeah, I feel like this kind of work for the medical AI systems or methodologies, there have been like around 100 products has been approved by FDA. So that may be something like you would call like how it can really be used or incorporated in the clinical protocol. But you can check their list. But I think in general, the current FDA approved methodology or AI model are very narrowed in the specific data modality or the specific application. So which means that only when you can narrow your application or what you claim it can work to a very specific domain, it may be reliable or robust enough that can be approved by FDA and can really be incorporated in clinical protocol. So for example, for the medical reconstruction, there have been quite a few like AI auditory models used to promote or to facilitate the medical image reconstruction. And I think for G or Philips, so one of their scanners just recently developed, they have incorporated the AI algorithms into their product, their scanning systems. And so you can say like, there is definitely something that is ongoing. And I think especially for like the collaboration or the research that is doing by the industry people, for example, in the Google Health or the Microsoft, like one of the, I don't remember the name, but they are especially trying to deployment in the real world product in the different clinical protocols. But from my point of view, even though this is very exciting and promising to see this kind of progress in the real world development, but we are still have a few questions that is unsolved and also unknown that will need more efforts from the researchers around the world to further investigate before we can, for example, to come into the final goal of a more generalist medical AI system.
Thank you very much. So let's thank all our speakers again, and